So, section 3.3, rates of change. We've had limits already, right? We've introduced and talked about limits quite a bit. And 3.2, continuity, was an application of limits, right? We defined very rigorously what it means for a function to be continuous based on our understanding of limits now. But in truth, in the grand scheme of things, it's sort of a bit of a side topic. Why we really care about limits is going to come into play in this section. So rates of change, I'll introduce this sort of geometrically. So there's two ways people often talk about rates of change. I'll tell you the other one in a second. But I'll go with this geometric interpretation, which is given a function f of x. So here I've drawn this function f of x. Consider what's called the secant line. And I haven't drawn the secant line yet, but consider what's called the secant line through 2 points on our curve. So I've just chosen two arbitrary points. I've said here's x equals a. So here's the point on the curve a, and the y value is f of a, right? The function value at a. And another arbitrary point, I chose x equals b, and I labeled the point on the curve b and f of b. So what is the secant line? Well, the secant line is just the straight line that passes through these 2 points. So that's all that a secant line is. You choose 2 points on a curve. The secant line is the straight line passing through both of them. All right, so there's our secant line. Okay, so what's so important about a secant line? Well, what we're really interested in is the slope of this line. All right, so I chose these 2 points. What's the slope of this secant line that passes through them? So slope of the secant line. What's that? Well, we've talked a lot about lines, right? Going back to review section 1.1, we talked a lot about lines. How do you measure the slope of a line? It's the rise over run, right? Change in y over change in x, or delta y over delta x. And what's that in this case? Okay, so I'll choose this point. I'll say my y value is f of b for this point. So that's f of b minus the y value of this point, f of a, over the change in the x values. And the x value for this point is b, the x value for this point is a. So f of b, oops, hopefully I said f of a, but I wrote f of b. So f of b minus f of a over b minus a. And there's the slope of the secant line. Okay, so there's our slope of the secant line, but what does it represent? Well, here's my function f of x, and you can think of this as x changes from a to b, my function changes, right? It changes from this y value f of a, it changes up to this value f of b. And of course, as I'm going along this curve, I'm sloping upwards, but it starts to get a bit steeper over here, right? It starts off fairly flat and it gets steeper and steeper and steeper. Well, the slope of this green line, the slope of the secant line, that expression over there, f of b minus f of a over b minus a, the slope of this line can be thought of as the average rate of change of the function, right? It's sloping pretty shallowly here, then pretty steeply over here, but it is the average change. So this is the average rate of change of the function f of x, f of x, as x changes from a to b. That is the average rate of change. We will soon ask questions about the instantaneous rate of change at various points, but for now we're just looking at it as x changed from a to b, my function values change from f of a to f of b. What's the average change as we moved along this interval from a to b? Well, the average is the slope of that secant line. So I will go with a physical interpretation of this for our first example, because everyone's used to thinking of, I think, in terms of position and velocity and acceleration and so on. So here's our example. The distance, we won't be fancy with this, we'll call it a particle. The distance a particle, oops, I won't erase, I'll just put an extra word in here. The distance of a particle from a fixed point is given by the following function. S, quite often in physics, if you have a function that represents position, you'd go with S, or distance. S of t is t squared plus 5t plus 2, where our variable t is time, of course, and its t is in seconds. Alright, so here's the question. Find the average velocity of the particle between t equals 4 and t equals 5 seconds. So a bit of a physics interpretation here. We're talking about average rates of change, right? And what is rate of change of position? Well, rate of change of position is your velocity, right? Your velocity is how fast you're changing position. So average velocity, this is asking us for average, right? Average velocity. This is asking us to find the average rate of change of position. And we have a position function, right? S of t is a function that tells us the distance of our particle from a fixed point. So rate of change of position, which is S of t. So this is what we're going to do. We're gonna measure this. We're going to find the average rate of change of S of t as t changes from t equals 4 to t equals 5. And what is this? We'll go back to our average rate of change formula, or the slope of the secant line. It's the change in the y values over the change in x values. Well, what are the y values? It's going to be s, our function, at t equals 5, right, at the bigger value. So we're going to take s of 5 minus s of 4. Right, so the position of the particle at time t equals 5 minus the position of the particle at time t equals 4. If you take their difference, you sort of got the distance that it's traveled between these times, over what essentially becomes the total time of this interval, right? So over 5 minus 4, right? It's an interval of 1 second. So we're looking at s of 5 minus s of 4 over 1. So we just have to plug these things in. Dividing by 1 is easy. We just need to plug in 5 and 4. If I plug in 5, we're going to have, I think we can just do this in our head, right? Plug in 5, we've got 25 plus 5 times 5 is 25, so 50 plus 2, we've got 52. Right, what does that represent physically? That tells me at time t equals 5, this function measures the distance of a particle from a fixed point. So at time t equals 5, it's 52 units. I haven't given you a distance unit. It's 52 units away from this point. Minus s of 4. How far away from the point is it at 4 seconds? Well, it's 4 squared, 16, plus 20, plus 2, that's 38. So time t equals 4 was 38 units away from this fixed point. Which is what? 52 minus 38 is 14. And there's our answer. The average rate of change of this function, which is the average velocity, right? Rate of change of position is velocity. The average rate of change of this function is 14 units from between, as our function changed from t equals 4 to t equals 5. Alright, so the book makes, I think, a bigger deal about average rates of change than I want to, because that's not calculus, right? That's just algebra, simple algebra, okay, slope of a line again. Nothing too fancy going on there. Here's where the calculus comes in, right? So we had the green line was the average rate of change, right? Well, the slope of this line is the average rate of change. It's the slope of the secant line going through these 2 points. The question is, what's the instantaneous rate of change right here, right? So x equals a, what's the instantaneous rate of change? And it certainly looks right here, right? The function has a much shallower slope than the green line. In fact, if I tried to draw it, it would just be this tangent line that touches this point, right? So it's, maybe it looks something like this, right? So this is the tangent line. And so let's write this. So instantaneous rate of change of f of x at x equals a equals, well, it would equal the slope of that red line, right? It equals the slope of this tangent line. What is a tangent line, by the way? I won't get into a formal definition of it, but it's this line that matches up with the intuition in your mind, right? It's a line that just touches this curve at a single point. And so it just touches it, and its slope sort of best approximates the slope of the actual function. So it's the slope of the tangent line to y equals f of x at x equals a. So the question now becomes, how do I measure the slope of this tangent line? Well, I can't do what I was doing with the secant line, because the secant line requires my line to pass through 2 points on the curve. Here I actually only know a single point on this tangent line. It's this point right here, a and f of a. So how do I find that slope? Well, here's the idea. So idea is measure slopes of secant lines with b closer to a. Right? What do I mean by that? Well, the reason the green line isn't a very good approximation of the slope of the red line is because I took b to be way out here, right? I took b to be this x value way out here. What if I make it closer, right? What if I choose, say, this point? Alright, so now I'm choosing my b to be right here. Well, if I took the secant line passing through these 2 points, so this yellow line, I think you'd agree that this yellow line, the slope of this yellow line, closer matches the slope of the red line than the original secant line did, right? So this is a better approximation of the slope of the tangent line if I measured the slope of this secant. How could I do even better? Well, again, I took b to be pretty far away from a. why not go closer, right? How about here, right? Take this secant line. That's an even better, if I took the slope of this secant line, that's an even better approximation of the tangent line, right? Well, it's still not the best. How could I do even better? Again, I've got all this room to work with. How about I take a secant line that's even, with this point B, even closer, right? So take it even closer. That's an even better approximation. How about I go even closer, right? Now I've got B really, really, really close to A in here. That's an even better approximation of the slope of the red line. And I can measure that, right? Because I know 2 points on this curve, I can measure the slope of the secant line. This is where limits come in, right? I keep choosing B values that are getting closer and closer to A. Why not take the slope of the secant line and then take the limit of that expression as B tends towards A? So this is exactly how we're going to define this. The instantaneous rate of change of this function, the slope of that red tangent line there, is we've got our average rate of change, f of B minus f of A, over B minus A, right? That measures the slope of all of these secant lines, depending on what value you choose B to be. And we've agreed that if I take B to be closer and closer and closer to A, I get a better and better and better approximation of the slope of the red tangent line. Why not take the limit of this expression? Take the limit as B goes towards A. So we'll take the limit as B approaches A. And this is the definition we're going to go with. So super, super important definition. So yeah, very important definition there, right? That's the definition of the instantaneous rate of change, and it's just based on this idea of, okay, I can measure the slope of the secant line. The secant line, the slope of this, becomes a better and better approximation of the slope of the tangent line if I let B get closer and closer to A. So why not take the limit as B goes to A? Let's see what happens as we get really, really, really close. That's a nice form for this definition, because it falls immediately out of this geometric interpretation. However, algebraically, when you're trying to work with this stuff, it's not the best. So I'm going to go with a slightly different form here. All right, there's our instantaneous rate of change. Let's go with a slightly different form. So alternate form. All I'm going to do here is I'm going to replace B with A plus H. Let B equal A plus H. Right? So every one of these points where I was choosing my B, instead of calling it B, I'm going to call it A plus H. Then what does H represent geometrically? Right? Well, H is the distance between A and A plus H, right? So it's this distance here. So what am I doing when I'm forcing B towards A? I'm forcing H down to 0, right? So I'm actually, this is the limit as H goes to 0. And now we're just going to plug in all the rest of this stuff. So if B is A plus H, what do I have up top? I've got F of A plus H minus F of A over down here, B is A plus H, so I've got A plus H minus A. What's A plus H minus A? Just H. And for algebraic reasons, when you're working with instantaneous rates of change, this is a much nicer formula to use. All right, so I'd recommend committing this one to memory and using this one forevermore. Awesome. Oh yeah, I will. I'll say one more thing. As before, we had the average rate of change of a position function is the average velocity. Now the instantaneous rate of change of a position function would be your instantaneous velocity, right? Alright, so here's our first example. It's find the instantaneous velocity of the particle from the previous example at time t equals 4. Alright, so we had our previous example, we had a particle, its distance at any time, the distance from a fixed point at any time t was measured, and this function s of t equals t squared plus 5t plus 2 tells us the distance at any time. Right, so in our last example we found the average velocity, right, the average rate of change of this function as time change from t equals 4 to t equals 5 seconds. This isn't finding an average velocity anymore, it's finding the instantaneous velocity at time t equals 4. Right, so what's its instantaneous velocity, which is going to be the instantaneous rate of change of this function. Right, so instantaneous velocity at t equals 4. Well, what's this going to be? Well, the limit as h goes to 0, right? This never changes. Of what? What do we have? We had f of a plus h minus f of a over h. Right, so what's a in this case? Well, a is the point you're looking at where you're trying to measure your instantaneous change. So a is 4. And our function isn't actually called f, it's called s, but it's just a name for the function, right? So we're looking at s of a plus h, s of 4 plus h, minus s of a, s of 4, all over h. Right, that's the expression we want to evaluate. So what are these things? Oops, I totally forgot to write the word limit. Limit as h goes to 0. And I do need this here, by the way. It's common for students to get lazy and stop writing the limit as they work through these expressions, but it really should be there to tell the reader or even to remind yourself that you're eventually evaluating a limit. Alright, so what does this mean? What does s of 4 mean? 4 means you're plugging in 4 everywhere you see t, right? I don't think many of you would struggle with that. But 4 plus h, all of a sudden, this quite often throws people for a loop. What is s of 4 plus h? It's the same thing, right? 4 means plug in, s of 4 means plug in 4 everywhere you see t. 4 plus h, s of 4 plus h, means plug in 4 plus h everywhere you see t. So s of 4 plus h is going to be 4 plus h squared plus 5 times 4 plus h plus 2. And so there's s of 4 plus h. Then we're going to subtract s of 4. So minus s of 4 is going to be 4 squared is 16 plus 20 plus 2. All over h. And unfortunately this isn't an easy limit where I can just plug in h equals 0, right? Why not? If I plugged in h equals 0, I'm dividing by 0. That always, always, always happens with these problems because you're always looking at something of this form, limit as h goes to 0, with an h down below, right? So that's always going to cause division by 0. It means I need to find some way to cancel it out. And the only thing I can possibly do here to try and cancel out an h from the top is simplify this whole thing, and hopefully something will factor. And so we'll go down that road. We will expand the entire top here, so we'll start foiling. 4 plus h squared, FOIL that out, 4 squared is 16, plus 4h is plus 8h, plus h squared. I'm not foiling that quickly, but check it if you don't believe me. Plus 5 times 4 is plus 20, plus 5 times h is plus 5h, plus 2. And here I need to distribute this minus 16, minus 20, minus 2, right? So minus 16, minus 20, minus 2. All over h. And some nice things actually happened here. I think a lot of stuff cancels. I've got a plus 16, minus 16. I've got plus 20, minus 20, and plus 2, minus 2. So the entire top actually became limit as h goes to 0 of just 8h plus 5h. In fact, let me write the h squared first. We'll count down in the powers. H squared plus 8h plus 5h is plus 13h all over h. What now? Still I want to cancel this h out on the bottom, right? That's always my goal. And I'm actually at the point now where I've got an h common to both terms up top, so I can factor that out, right? This is the limit as h goes to 0 of h times h plus 13 over h. And I've actually done it now, right? H multiplies everything on the top, h multiplies everything on the bottom, those guys cancel. And I'm looking at just the limit as h goes to 0 of h plus 13. So the limit of this complicated looking expression actually reduced to the limit of this very simple expression. And now there's no problems with h going to 0 there, right? It's very clear to see what happens. Here it wasn't clear because I divide by 0 as h goes to 0. But over here, as h goes to 0, h plus 13 is just going to let h go to 0. It's 0 plus 13. So this limit is 13. And that is the answer. That's the instantaneous velocity of this particle at this time t equals 4. This is why you need to be good at algebra, right? The calculus is just this definition. That's all that the calculus is. Everything else, going from here down to here, that's all algebra in between, right? And it's why you need to have good algebra skills in a calculus class. The good news is that this is a very long-winded way of getting this answer. As we go through this course the next couple of weeks, you will see lots and lots of shortcuts that will allow you to go from this question, find the instantaneous velocity, to getting this value 13 in probably about 10 seconds flat. So there are shortcuts, but we're not quite there yet, right? We've only just introduced what instantaneous rate of change is. Alright, so we'll do one more example in this section, coming back to tangent lines. Find an equation for the tangent line to this curve, y equals 5 over x, at x equals 2, or when x equals 2. So I'll give you a really quick sketch of what this looks like. 5 over x actually has 2 branches. It looks a bit like this to the right, and it's got this piece over here that we're not going to be too concerned with. But more or less, this is what 5 over x should look like. How do I know that? Well, because like I said, it's good to have some basic graphs in your mind memorized, and this is what the graph of 1 over x looks like. So 5 over x just multiplies everything by 5. It looks basically the same. And we want to come in here. We've got 2. What's the y value here? If this is 2, what's the y value? Well, it's 5 over 2, 5 halves. I'm not going to go with decimals. I could write that as 2.5, but fractions are so much nicer to work with. So I'll keep it as 5 halves. And we want, here's my tangent line. Should have the same instantaneous slope as the function. We want the equation of that line. So go back to lines. Go back to lines in your mind. What did I say we need to write the equation of line? We always need 2 things. We need a point on the line. We need a point. Do I have a point on the line? Sure, I just found it, right? If x is 2, y is 5 halves. So here's our point, 2 and 5 halves. And 2, we need the slope. What's the slope? Well, the slope is the instantaneous rate of change of this function at 2, right? So what's the instantaneous rate of change of the function at 2? It's the limit as h goes to 0. Again, this form never changes, right? You should have this formula memorized. Limit as h goes to 0 of f of a plus h minus f of a over h. Right, there's the general formula. What are we choosing a to be in this case? We're choosing a to be 2. All right, so this is limit as h goes to 0 of f of 2 plus h minus f of 2 over h. All right. Again, what does f of 2 mean? F of 2 means everywhere I see x, I plug in 2 for x. What does f of 2 plus h mean? That means everywhere I see x, I plug in 2 plus h. So this will be 5 over 2 plus h minus, right, that's f of 2 plus h, minus f of 2 minus 5 halves over h. Now what am I going to do? Well, for starters, I'm going to make myself some space. And we're just going to bring this over here. So as always, I'm in this position, I can't just plug in h equals 0 because I'm dividing by 0 if I do that. So what I have to do is try and simplify the top somehow and get an h to cancel. So what can I do to simplify the top? Well, anytime I have two fractions, quite often I want to combine them into a single fraction. So I'll try to do that here. I need them over a common denominator. Let's just go with the common multiple of these denominators, so 2 times 2 plus h. So we've got 5 over 2 plus h. I want 2 times 2 plus h, so I'd multiply the bottom by 2, I'd multiply the top by 2. Minus, we've got 5 over 2, and I want 2 times 2 plus h, so I multiply the bottom by 2 plus h. I had better, if I can make it a little bit more space here, I'd better, we had 5 over this, I'd better multiply the top by 2 plus h. So they're over a common denominator now. So this is now the limit as h goes to 0. What do I have? I've got 10 minus, let's just distribute this as we go, minus 5 times 2 plus h, so that'll be minus 5 times 2 is minus 10, minus, remember to distribute this negative here, minus 5 times h is minus 5h, all over 2 times 2 plus h, and that whole thing is still divided by h. And this problem was taking up a lot more space than I was expecting, but that's okay, we'll just keep coming over here with this. Limit as h goes to 0. Because this is taking up so much space, let me just do this on the fly here. What does this mean to divide a fraction by h? Well, how do you divide into one fraction by another? You flip it and multiply. You might say, hold on the bottom here I don't have a fraction. Well, I really do, right? H, I can write that as h over 1. Now if I divide by h over 1, that's the same as multiplying by its reciprocal, right? So the reciprocal of h over 1 is 1 over h. So what does that mean? That h down below, dividing by h, actually just puts the h in the denominator here. Right, so 10 minus 10 is 0, minus 5h is minus 5h over, so the h ends up down here, I write it on the outside, I write 2h times 2 plus h. I still can't plug in h equals 0 because this h still lives here, it still lives on the bottom, it's still causing me to divide by 0 if I plug in h equals 0, but we are at the point now where I've got the entire top is multiplied by h, the entire bottom is multiplied by h, so they cancel. So this is the limit, as h goes to 0, of minus 5 over 2 times 2 plus h. And this puts us in a good spot, right? Why? Well, if h goes to 0, I don't divide by 0 anymore, right? So I can freely do this. As h goes to 0, this is tending to, well, just let h be 0. It'll be minus 5 on the top over 2 times 2 plus 0. 2 times 2 is 4. So that is the instantaneous rate of change of this function, 5 over x, at x equals 2. And it's our slope of the tangent line. And so not much work went into finding the point. Right, finding a point on the line, we just had x equals 2 when we found the corresponding y value. But quite a bit of work did go into finding the slope, right? We had to compute the instantaneous rate of change of the function at x equals 2. But now that we have that, we have both ingredients we need to write the equation of a line. Now we can go to it, right? It's y minus y1 equals m times x minus x1. And we'll plug these things in. Y minus y1, y minus 5/2, the y coordinate of the point on the line, equals m minus 5/4 times x minus the x coordinate of the point, 2. And I'm happy to leave my answer in this form. Again, if my math lab says give your answer in the form of y equals something, well, you just add 5/2 to both sides. And probably distribute this out and simplify. But yeah, there's an equation for the tangent line. I've erased it at this point, but it was the green line. And yeah, I think this section is getting pretty long at this point, so we will we'll stop here. This is a big deal throughout calculus. We will do this type of stuff again and again and again, but as you've seen so far, it's a little bit tedious, so we'll come up with faster, shortcut ways to do this stuff. Thanks.